Announcements. So obviously you guys just collected your test papers. So that's for test 2. And of course we've got the third test coming up, test 3. So let me give you some context. So today we're going to be talking about rigid body dynamics, right, in general. And what falls under rigid body dynamics is a kinematics component and a kinetics component, right? So this is mirroring what we were learning in week 7 and 8 on particle dynamics, basically. So particle dynamics was split up into kinematics and kinetics as well. Basically, what I wanted to show you guys in that email is I asked Wei, alongside the other tutors, just like copying them in, whether rigid body kinetics will be in quiz 3, so your upcoming test next week on Saturday. Because I saw that it was part of the workshop examples, but it's not in any of the practice papers. So if you look on Moodle, it's not in any of the sample papers, basically, right? And so he replies, we don't need to specifically exclude rigid body kinetics, as all the dynamics content could be tested. We cover rigid body kinetics in the workshop and lecture. So take of that what you will. Pretty much it's ambiguous, that answer, to be honest. I know for a fact rigid body kinematics is shows up a lot in the sample papers, but rigid body kinetics, whether that's in or not, is based on this response in the email. Okay, so take of that what you will. So with that in mind, how I've organized my notes is I'm going to focus on the rigid body kinematics, right? And during your studies, you should focus on kinematics, right? So between this week's content, focus on this 80% as you're studying. The majority of what you're studying for this week's content should be for rigid body kinematics. But I would say don't neglect this, right? Still spend some time, brushing up on your kinetics as well because of that email. Okay, so I've included my notes for it, which are in the tail end of this document, the second half of this document, basically, for it, okay? So let's just distinguish between those two things, right? So kinematics, right, is essentially thinking about the velocity, right, and the acceleration of rigid bodies. That includes the rotational and the linear, right? So we're also interested in just the linear velocity and acceleration. So we'll talk about that today. Kinetics, on the other hand, is focusing basically on Newton's second law, so F equals ma, but in the context of rigid bodies. So this is the equation of motion, and there's another version of it that looks similar to this, but specifically for moment, right? And so instead of ma, the moment, equation of motion focuses on the mass moment of inertia multiplied by the angular acceleration, okay? And there's ways we can figure out the mass moment of inertia as well. So that's all included in my notes. And there's also going to be work energy and impulse momentum methods that are going to be applied when you have something that's moving not only translationally, right? So when I say translationally, I'm talking about in particle kinetics, we're talking about let's say a ball that's moving or whatever. We're just focusing on the translation of it, right? So yeah, that. But if we have, say, a rod, so a 1D rigid body, and it's pivoting around a hinge or a pin support, it basically has a center of gravity, and it can rotate and, well, this one's just rotating, but yeah, there can be cases of rotation and translation, basically, right? Okay. So yeah, when we're talking about work energy methods and impulse momentum methods, there's going to be two components. There'll be rotational and translational. Okay, so I'm going to give a little recap on relative motion, because we kind of glossed over this in week 7, because in week 7 I was trying to teach particle kinematics, but it was largely overshadowed by the quiz 2 that you guys had, which didn't have any dynamics on it, right? The quiz 2 had frames and stuff you were more focused on. So I would like to talk about relative motion because it's going to be important for the rest of this workshop when we're talking about rigid body kinematics, all right? So just recap, relative motion, imagine you've got two cars, for example, and they're orientated like so. You've got one car moving due west, let's say this is plan view or top down, and you've got another car that's moving with a velocity vector like so. Let's call this car's motion VA, and then let's call this car's motion VB, right, the velocity. Let's just say, for the sake of this demonstration, and I'm just going to rotate this slightly, that the horizontal component of that velocity vector for object B is the same size as VA, okay? The horizontal component only, right? So if we were to draw these vectors tip to tail, right? So we're drawing VB and VA, sorry, not tip to tail. If we drew it originating from the same point, right, like so. Okay, so there's this point of origin for both of these velocities. What we can do is basically imagine one of these as having like a camera on it, or like a point of view that you're viewing it from, right? So in this first case, this expression that I've drawn out, I'm basically saying the velocity of A is equal to the velocity of B plus the velocity of A relative to B. So you have to get familiar with this subscript. A/B means A relative to B. And when I say that, I'm talking about B, or the second thing that you write on the subscript, being the point of reference, right? So the POV. And so if my point of view was B, right, like in that first expression, an arrow that connects from B to A represents VAB, right? So this has to be like a closed loop, right, for this triangle. And yeah, so you're originating from B and you're going towards A. Okay, so what does this mean physically, right? So we have the two cars, right? And, you know, you got your velocity of A and you got your velocity of B, which I'll do in orange. If you were sitting in car B and you looked at A, right, it would look like it's just moving up, right? Because if you're matching its horizontal velocity in terms of your magnitude and direction, yeah, the only difference would be that car A, right? Pretend this one was completely still. Car A looks like it's doing that relative to you, right? So that's what the velocity of A relative to B means, okay? And if we were to think of it from the other perspective, right? So velocity of B is equal to the velocity of A plus B relative to A. Okay, so what does that one mean? So again, if they're originating from the same point, right, but now we focus the camera angle on A, right? So what's the velocity of B relative to A? It looks like B is just moving down, right? So as these cars are driving, it just like, and if you're sat in this car, it looks like B is just moving down. Does that make sense? So that's relative velocity. Let's do a quick question just to refine our understanding. So yeah, you've got these two cars, right? Car A is moving east, right? So this one's car A. And then car B is moving due south, right? And car A is moving at a constant speed, right? So it's got a fixed velocity and it's moving at 36 kilometers per hour. So we're gonna need to make a note of that and convert it to meters per second later. And then car B, it starts from rest and then it starts accelerating at 1.2 meters per second squared. And so ultimately what we're interested in is finding the relative velocity and acceleration of B. So VB with respect to A, okay, and AB with respect to A. So that's what we want to find, and specifically this is at time is equal to 5 seconds. Okay, so why that's important is because it's going to, sorry, the velocity is going to be changing, right, based on time. It's going to slowly increase over time, and so at 5 seconds there'll be a certain velocity, right? This is for car B, right? Okay, so let's do a quick recap on, these are the wrong way around. Let's do a quick recap on unit vectors, right? So if we're looking top down, I'm just going to assign unit vectors, right? So moving in the positive x direction is I, right? And then moving in the positive y direction is j, right? So unit vector of I and the unit vector of j. So basically, if we were to think of it in terms of these unit vectors I and j, what this is saying is that the car A is moving 36 of these directional vectors of a single unit to the right, but it's in kilometers per hour right now. Whereas, car B is accelerating at negative 1.2 j. Negative because it's pointed down, so opposite of the positive direction conventions. Okay, so when we're converting from kilometers per hour to meters per second, remember that we need to do some stuff with kilometers and we need to do some stuff with the hours, right? So if you want to convert hours to seconds, you need to go to minutes and then to seconds, right? So you have to multiply by 60 and multiply by 60. And then for kilometers to meters, you need to, multiply by 1,000, right? And then this is like some fraction, basically, right? So what this boils down to is either multiplying by 3.6 or dividing by 3.6, right? To get one way or the other, right? And if you want a quick way to think about it, the way that I like to think about it or memorize it is if you've got 36 kilometers per hour, that's pretty close to how fast you're moving in a school zone, right? Around 40 kilometers per hour. So if I was to get 36 kilometers per hour and then multiply by 3.6, that's telling me that we're going over 100 meters per second in the school zone, right? And if you think about that for 1 second, that makes no sense. That means like you'll probably kill someone, right? So this is a good benchmark for like the physical interpretation of these numbers. That tells me that if I want to get from kilometers per hour to meters per second, I just divide by 3.6. Okay, does that make sense? Yeah. And so you get a more reasonable number, and that number being 10 I units meters per second, okay? Unit vectors. So car A is moving at constant speed, so there's no acceleration. Whereas car B, it starts from being still. So we're going to use our Suvat equations, right? So that's to do with speed, displacement, initial speed, acceleration, time. This one specifically, right? So we're interested in finding this function for the speed, and the initial speed is 0 meters per second because your car starts still, at least for car B. And then we're told that the acceleration of B is negative 1.2 j, right? And then that's multiplied by the time. Okay, so if I write this, this is basically saying this is the function, right? And so this is, the speed will be a function of the time somehow, okay? So if I was to plug in t is equal to 5 seconds, basically I get that that the velocity in this instance of time is negative 6j, right? Meters per second. Okay, so for the velocity vector, right? Oh, sorry. This is the relative velocity function, right? Or expression. We know what VB is, right? We just calculated it. We know what VA is because we converted to meters per second now. And you can see that these are in different directions, right? So VB is in the negative y direction and VA is in the positive x direction, right? But you can actually add these together if you consider it as vectors, right? And so if we were to rearrange for the speed of B relative to A, we basically just move 10 onto the other side, and that simplifies to negative 10I. So what I've done is I've just I've put the unit vector I out the front and the unit vector j at the back. Okay, and that graphically is represented like so, right? So if I was to draw the tip to tail triangle, right, it starts from this point of origin over here, and then A goes to the right, B goes down. Okay, and now we're interested in the velocity of B relative to A. That means my camera starts at A, and it's pointed towards B, right? And so that is going to be the magnitude of it. And this vector, right, is broken into its horizontal and vertical components, and they're both negative, which to me implies that it's an arrow facing down and to the left, right? Okay, does that make sense? Yeah. Okay, so this is all relative velocity in terms of particles, right? I'll tell you how this is relevant to rigid bodies in a second. Okay, now that was one part of the question, right? It asked us for the relative velocity of B, the velocity of B relative to A. Now what about the acceleration? So we're told that B accelerates at negative 1.2 J units, right? Whereas car A does not accelerate because it has a constant velocity. And so therefore, when you have one of the two objects not accelerating, it means that the relative velocity of, that the acceleration of B relative to A is equal to just the acceleration of B, because the other one's not accelerating, right? So yeah, that's negative 1.2 J. Okay, and that's in meters per second squared. So that was the second part of the question, and that's what they were asking from us. Okay, I might have gone a little quick, but does that kind of give a like a basis for relative velocity for you guys? Do you
just go back on when you covered
up here?
B over A, when you had that triangle before? Go down.
Yes.
Why is J negative there?
Why is J negative? Oh, so let's just make this a little neater. Oh, why is I negative? So if you have a downwards and left facing arrow, yeah, the positive directions for I and J, remember, are this way. So they're both negative. So if you're going down and left and up and right, so if up and right is positive, down and left is negative, right? Does that make sense? So, okay, this is the positive direction that I'm
confused when you wrote that VA.
So VA is 10I, just means 10 is the magnitude and I is a unit. So imagine 10 Lego blocks going to the right. Okay, and then this one's 6 Lego blocks going down. Yeah, so if you break this arrow into those components, like those units, then that's the travel. Okay, so another way you can think of it is, yeah. The diagonal is basically just made up of, so 10I is this part of the diagonal, right? And then 6J is just this part of the diagonal. So you've got a horizontal and vertical component. Yeah, no problem. Okay, any other questions? No? Okay. So that's in terms of particles. Let me just recap on rigid bodies. So I've kind of alluded to the concept of rigid bodies a couple times throughout this course, but I might not have really formally explained it. So let's just do that now. So when we're doing physics with any kind of object, you need to understand the physical interpretation of the object we're dealing with in terms of its maths. Okay, so you got your different objects, and there's basically 3 types. One I haven't written here. The other one is flexible bodies. I'll explain that in a second. So particles, right? Let's just say we're throwing a ball. Okay, we define the kind of coordinates of like x and y, for example, which marks out the directions which we're considering the movement of the ball, right? But the ball itself is just a point in space that's moving. Okay, we don't actually care like the diameter of this ball, or these kind of other dimensions, right? It effectively doesn't have a size when we're doing something like, for example, projectile motion. It's just a point in space that's actually just moving, right? And we can, and when we were doing in week 7 the particle kinematics, all that really means is we're treating our physics object as a particle, so we don't care about its dimensions, we just care about its spatial coordinate, right? And how it's going to move. So kinematics refers to, you know, V and A and S and T and all that, right? Okay. Rigid bodies, on the other hand, actually have some kind of dimension that we're considering, right? So you can go into 3 dimensions. You can consider a one-dimensional rigid body. So for example, a rod like this. And actually earlier in the course, we were already doing maths with rigid bodies, 1D rigid bodies. We were doing beams, right? And in our beam analysis, we cared about, in our beam static analysis, we cared about the length of the beam, or like, for example, how far along the beam a force is applied so that it induces a bending moment, for example. So we've been dealing with rigid bodies since week 2, pretty much. You can also get into 2 and 3D rigid bodies, for example, like a rock, right? And it's got a center of mass over there, and etc. And then 3D would be considering all 3 dimensions, for example, of this rock, right? But in today's lesson, we're going to mostly deal with 1D rigid bodies, and some of the questions you'll see, there'll be multiple links of these rigid bodies, so there'll be like multiple links of rods. I'll explain how that works in a bit, but yeah, we're just dealing with 1D rigid bodies today. Flexible bodies, on the other hand, would be like if instead of a rod you had like a spring, for example, that could deform. That would be a flexible body, for example, right? But we don't deal with that, at least in this topic, okay? We're only concerned about this as a rigid object that can move in space and rotate, but can't squash and stretch. Does that make sense? Okay, that's rigid bodies. The other thing is plane motion. So if you think about it, right, there's kind of 2 components to rigid body motion. There's the translation component, and then there's a rotation component if you consider it about a fixed axis. So what do I mean? So for example, if you have a car and it's moving, right, this is translation, okay? If you have something like a windmill or wind turbines or whatever, and it's got a fixed axis, like in the middle there, as you can see, and it can spin like this, right? So this is rotation. So general plane motion is what a lot of more complicated systems undergo, right? A combination of translation and rotation. So for example, we've got this dude's arm, for example, and let's say that's, you know, a pin and it's rotating as it's walking. It's rotating about, it's like shoulder blade or whatever. And at the same time, the whole like person is moving, right? So anyway, general plane motion is the combination of translation and rotation, basically, right? Okay, so before I get into today's meat, like the meat of today's topic, I guess, okay, I'll tell you what we're gonna dive into, right? Velocity dynamics and acceleration dynamics, okay? So this will be what, so the overall topic is rigid body kinematics, right? Okay, and then, yeah, this will be further broken down to velocity dynamics and acceleration dynamics. So in order to do acceleration dynamics, you need to master velocity dynamics, okay? So that's the first thing. So we're gonna talk about velocity dynamics. In terms of the methods, to solve problems, right? For velocity dynamics, we have 2 methods you can use. The first one is called, it's just relative motion. So that's where what I was talking about before hopefully will come into play. And then the second one is called the instant center of rotation method. Instant center of rotation, okay? And for acceleration dynamics, we also deal with different methods. Oh, sorry, there's essentially only one method you can use. It's relative motion. Okay, so both of these require relative motion, but there's a little trick you can do if you wish for velocity dynamics, which allows it to be a little bit easier if you understand it properly. Okay, so I'll give you a quick like analogy back to when we were doing beams, right? When you're solving for the internal forces of a beam, I told you that there was two methods that we can really use, right? The first one's like a graphical method, and the second one's like an algebraic method, right? Now, different people call these different things, but the graphical method basically was faster and easier to do, right? Whereas the algebraic method was more thorough, but a little bit harder to understand at first, right? So when we're doing this topic, right, for velocity dynamics, relative motion is actually the harder one to understand, but it's actually the one that I want to teach you first, right? Because to do the instant center of rotation method, which is kind of easier and faster, you need to understand where everything comes from, okay? And relative motion is where everything actually comes from, okay? So I'm going to teach you this one first. So when we're doing the questions, so just keep in mind, this relative motion question in the context of particles was question 1. So question 2, which I'll do in a bit, is going to be velocity dynamics relative motion. Question 3 will be instant center of rotation. And then question 4 will basically be an acceleration dynamics question, which uses the instant center of rotation to find out the velocity dynamics. So it's always, so to do anything to do with like acceleration dynamics, you need to have solved for the velocity dynamics anyway. Okay, in terms of the actual skills we need, right? You'll find that this topic is actually going to be probably the hardest topic in the whole course, okay? And you may have come into like week 1 and 2 of this course pretty confident, and then you do your quiz 1 in like week 3 and stuff like that. And it's like, oh, this is easy. It's like, how's this course gonna get hard? I'll tell you how it gets harder, right? So it's from this topic. So the reason it's hard is it requires you to draw a lot of skills from various parts of maths and physics and other parts of this course in order to solve these kind of questions, right? So where do I start? Okay, so first thing is geometry, right? And from geometry, you solve angles, right? Okay, you might be thinking, from week 1, we solved right angle triangles constantly, right? So for example, if you have like a force that represents, like a diagonal force that represents like a hypotenuse of a right angle triangle, for example, you could find its individual components, right? Its side lengths through your understanding of sine and cosine, right? So that was fine. I guess one thing with this part of the course is we're going to deal with triangles that are not right angle, okay? So therefore, in order to find these angles, and let's just call these side lengths A, B, C, and let's call the angles that represent the opposite corner of the side lengths, alpha, beta, gamma. In order to work out these angles and side lengths for a non-right angle triangle, we need to go back to high school geometry and use sine law and cosine law, right? So I'll give a recap of that in a bit. Okay, so that's the first thing. The second thing is relative motion, and kind of that introduction from particles, right? And the other one is understanding circular motion. Okay, so these are both, well, they were both introduced from our week 7 kinematics topic, right? Particle kinematics. So it's gonna be an extension of that, right? That's another thing. Okay, and then the other thing is understanding vectors very well. So this is from maths again. And basically understanding vector multiplication. So let's just call that vector multiplication, which is, I guess, from maths 1A. You've got your dot product, versus cross product. Okay. And also understanding unit vectors. And that will come up if you decide to use the cross product method, okay? Anything else? I think that's pretty much it. But yeah, anyway, it draws from various maths and physics topics and like, yeah, stuff that you saw earlier in this course, right? So that's kind of the difficulty of this, okay? Yeah, any questions so far? All right, let us, I'm going to explain velocity dynamics. Let me give you guys a break. Oh, velocity dynamics and angles. Okay, so yeah, velocity dynamics, a lot of the time that is just referring to, we're interested in finding the linear velocity of a certain node, I guess, or we're interested in finding the angular velocity of how like a hinge is rotating, okay? So let's just start with a simple scenario, right, of rotation about a fixed axis, right? So I want to familiarize you guys with notation. So if you imagine something like a pin support or hinge that a rod can rotate about, this rod, let's consider it as rigid. Okay, so this is a fixed distance. Okay, and we're going to call that distance ROA. Okay, so that subscript might seem at first as like kind of arbitrary because, for example, if I had a beam, right? So going back to the beams part of this topic, if I had a beam and the length, oh, sorry. Okay, so you've got nodes, right? You've got node A and you've got node B. I might choose to call that length of that beam, you know, let's just say, for example, LAB, or I could call it LBA, and ultimately it doesn't really matter what you call it. So if you wanted to, yeah, like refer to that beam length, I guess, or if you wanted to refer to that member, right, it's kind of arbitrary, which like, yeah, order that you say. It's more of a distance than like a displacement or a lever arm or anything like that, right? Okay, but what I'm trying to say is that this behaves more like a lever arm, or it's kind of important, like the start and end points, right? So when I'm saying R or A, I'm literally referring to, pretend this is a vector, or it is a vector. There's a vector that starts from O and then ends at A, okay? And it represents like a lever arm. Okay, so this should kind of remind you of an earlier kind of scenario, right? When we were doing, let's just say a beam, okay? So let's say you've got a reaction over here, By, and you've got a reaction over here, Ay, and you apply, oh, sorry, and you're doing the sum of the moments, for example. So we're doing static analysis. Sum of the moments about A is equal to O, so it's an equilibrium. And we were interested in finding the moment that's induced by reaction By, right? And then, you know, let's call that R, right? So that's the lever arm. So we've got By, force, and you multiply it by the lever arm, right? And then we basically visualize whether it would cause a clockwise or counterclockwise rotation, right? So this force is going to cause a counterclockwise rotation, and therefore this value is going to be positive. So what we're doing here is like a moment, right, is actually like a force cross product a lever arm, right? But effectively what we're doing is we don't care that it's a cross product because we're kind of doing this, right? We're kind of dot producting it. And just for context, right? If you have a cross product, right, and all of these are directional, versus a dot product. So I'll give you an example of a formula where we use a dot product, like the work formula is a dot product, right? So these are two vectors, right? The force is a vector and the distance or the displacement due to the work done is a is a vector, but when we do a dot product, it gives you a scalar, right? So anyway, it's kind of weird to treat it almost like a dot product, but basically that's how the maths kind of works when we do this, because we're doing it from like a how do I say it? Yeah, we're kind of fudging this, right? Because in reality, this is a cross product of two vectors. We're kind of doing it like we just care about the magnitude, and then we determine the direction afterwards, right? Right. We keep this as a directional thing, quantity, but we just say plus or minus based on whether we get something that's counterclockwise or clockwise, all right? You know what I'm saying? So that's kind of how we've been doing it earlier in this course. And that's kind of what I'm going to show you for the first half of this workshop. And then towards the end, I'll show you how I go about doing cross products if you so choose to do cross products. Okay, anyway, my point is, this whole moment force and lever arm relationship is very similar to the relationship for angular velocity, except for moment we basically did m, and then you do the cross product between v and r, except not v and r, f and r. But for the angular velocity, we do the velocity divided by the lever arm. Okay, so that's kind of how this formula works. And so we can also rearrange this for velocity, and you get this. Okay, so yeah, what else to explain? Okay, so what we kind of do is basically if you have angular velocity like so, then and there's this point that's fixed, right? So point O is fixed. The other end of your rod, let's call that point A, the velocity can only be tangential to that lever arm, okay? Or it can only be tangential to the rod. In other words, if you've got a counterclockwise angular velocity, it's going to result in a linear velocity of A that's 90 degrees to the rod. Does that make sense? So on the other hand, right, for example, if the rotation was going the other way, right, the angular velocity, then VA would be pointed 90 degrees from the lever arm, but going the other way. Okay, so you always know the direction is 90 degrees relative to the lever arm. Okay, that's one thing. Okay, and the other thing is pay attention to all these subscripts, right? The lever arm, we're projecting this from O to A. The angular velocity, we're doing the same thing. So O and A, which is saying like it's rotating about O, right? And we're concentrating on A. It's just rotating about O basically is the most important part. Okay, and then for the other end, right? Currently I've just said VA, but I'll tell you why that is. It's because if you have this formula for VA, and it's the relative velocity, you've got the velocity of A is equal to the velocity of O plus the velocity of A relative to O. Okay, so what does that mean? Well, it's from the relative velocity formula, but then if one of the ends is not moving, right? If this point's not moving, then this just becomes equal to this, okay? And so in all of these formulas, in reality, the linear velocity is always the relative velocity. But in this particular scenario, VAO is equal to VA, okay? In the case of one of the ends being fixed translationally. Does that make sense? Kind of. I'm just trying to get you to be able to look at it from different angles at the moment. I'm talking about it pretty theoretically though. But yeah, hopefully that kind of makes sense. So these are all kind of concepts I want you to think about. Okay, the other thing is if instead of looking at everything in terms of this like counterclockwise, clockwise spin, right? Like for example, moment was a spin. If we had like angular velocity around a hinge, this is like a spin. So spin referring to like clockwise, counterclockwise. Okay, but if instead of doing that, we thought of everything in terms of unit vectors, okay, and the whole like cross product thing, what we need to do is visualize 3D space. Okay, you've got x, y, and z. Z coming towards you and out of the page, right? And what we're saying is that we've got unit vectors of I representing x, j representing y, and k representing z. So positive k is coming out of the page and at you, right? And that represents the positive z direction. Okay, and so why is that important? Well, it's because that is in reality what these kind of spins are, right? So if we were to do it in unit vectors, a counterclockwise spin of omega, or of angular velocity, is actually pointed in the positive z direction. Okay, in other words, the positive k direction. Okay, so this is called the right hand rule, because if you look at your hand and you curl your fingers, right, where your fingers are curled towards, the direction your fingers are curled towards, it's pointing counterclockwise. And it's basically saying to you that coming out of the page, or the positive z direction, the positive k direction, that is actually representing a counterclockwise spin. Does that make sense? Right? So positive z equals counterclockwise. That's what I'm trying to tell you. Okay. So this will be important in the last question when I'm talking about doing cross products, because the cross products will involve the k unit vector, or the z dimension. Okay. Okay, so that's a lot of theory. Oh, a bit more theory. Okay, I've got a bit more, and I'll give you guys a break. Okay, I promise. Yeah. Yeah, for sure. Yep, this one. Yep, here's how I like to draw it, right? And if I was to overlay this, then it'd be like thumb, finger, 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 like that. Okay, it's the right hand rule. So if you're curling your hands counterclockwise, it's referring to positive z, positive k direction, right? Okay, any other questions for now? Okay. Are you all good, by the way? Okay. Okay, so I want you guys to understand general plane motion. So general plane motion, as I mentioned before, is translation and rotation combined. Okay, so the easiest way I can, so I want you guys to focus on the physics, not the maths at the moment, right? I want you to understand general plane motion. Okay, so the best thing I can do is kind of draw like a little animation for you that you can just visualize. Okay, so if this rod has to be fixed, so this distance between these two objects, A and B, which are sliding on these fixed paths, right, has to be fixed, then basically this one's moving to the right and this one's moving down, right? And so the animation over time, through time steps, looks something like this, okay? Does that make sense? Right. And if we're interested in what VA is, right? So if VB is a known quantity, we're interested in VA. And we know that what I just drew is like A would follow this path down the shaft, correct? Okay. But what I'm about to tell you is that that path I just drew is going to be the sum of two components, okay? The first component is translation, okay? So it's basically the path is moving to the right, okay? Now, that might not make any sense at the moment. I'll tell you why this is, okay? This looks like it's incompatible, aka how can the slider move to the right, okay? But the truth is, it's because I'm only showing you half of what the final result is, right? So keep that in mind. So there's translation, okay? And that translation follows VB. And the other one is, imagine point B was actually fixed in terms of translation, but it was allowed to rotate, right? And so this would be the other animation. Okay, so this rod, again, it has to stay the same length, right? So it can't squash and stretch, but it's allowed to defy the path a little bit, because when you add this one, okay, so let me draw that again. So this path, okay, is equal to this plus this. Okay, so this was the starting point for all of them. Does that make sense? So this downwards motion is the rightwards motion plus this circular arc of rotation. Okay, so that is basically what I'm trying to say. So general plane motion, which is this, is equal to the translational component, right, which is moving to the right in this case, plus rotation, which rotates counterclockwise in this case, okay? So what we're doing in the rotation component is we're pretending that point B is fixed, okay? And then, yeah, like your object A is just rotating counterclockwise, okay? Spinning counterclockwise relative to that. Okay, I'll give you guys a break. And then, yeah, we'll go for 5 minutes. I'll come around in case you have questions, all right? Oh, wait. Oh, you have a question? Oh, yeah. Did you want to collect your paper? Yeah. What's the step? A is
Gas.
Oh, sure. Can, but I'll just get through my question because
Yeah. Sure. I'll just wait until
might take a while. So this component is basically saying, just imagine it as if the beam was not completely still. And then like a circular path that A follows.
So if this one is what is the translation out of
Okay, so this what I'm describing is following this expression. If I want to flip it, so VB is equal to VA, right? What I do is for the rotation component, I flip the subscript to be relative to A. Okay, and so what that will look like is we're interested in the movement of B. Yep, that one. So that's that one. And that's going to be equal to the velocity of A, right, which is downwards. That, right? Plus, we'll fix A this time. Okay. So this one's just rotating like that. Sorry, let's rotate the other way.
So the translation
track everything.
Translation is rotation is
It's okay.
I'll give you this if you want to look at it, but this is the other way around.
I did, that's what I said. I don't know how you define the page. Is that just because we're analyzing everything in 2 dimensions?
Okay. That's easy. Do you have other questions?
Located process of elimination. I can't remember.
you guys have any questions?
Yeah, I was a bit confused. Like, I thought you were going to explain.
Yeah.
Just like what you were explaining here with your animations. I don't know if you can get weird.
No, that's great. Great. It's weird. So, wait, this is a perfect example. So, what do you make? Oh, it's not working. Look, we join it into this explanation. So, this red line that you drew, right? The problem with this. Oh,
I didn't quite get it.
she wanted a re-explanation of this line, right? So, the problem with this is you can't shrink your rigid body. So what you've drawn is actually part of this, right? But this is incompatible because this line is longer here than it is down here. Correct. So they have to be the same length. It has to actually move like that, right? That's the first thing. Okay. The second thing is yes, this. Oh, sorry. The general plane motion has to follow that shaft or whatever. It's a constraint. Okay, so that's the second thing. So that's the GP motion. That's equal to two parts, right? Now we're allowed to go outside the boundaries of the shaft if we're looking at the individual components, right? So just the sum of these two is those parts. Yeah, but if we look at the individual components, they're gonna like fly out of the maze path or whatever, right? So it's gonna look funny for a second, right? But what I'm trying to say is that the translation of A is actually going to be this, which is following the velocity of B. Plus, if you at that point and you fixed it, it's just like if B is equal to 0 there, right? And then it's rotating. Right? So what this is saying is that if you do this and you add it to this, it gives you the distance between A and B are the same. That's part of the you can't change that. So when you're doing 1D rigid body kinematics, the two ends are treated kind of like particles, right? So the two ends, right, A and B are treated kind of like particles, but they have a fixed distance between them. That's like the main thing. Anyway, sorry, this still might not make any sense, but mathematically, you'll see. Maybe it'll make more sense. But VA is equal to VB plus VA relative to B. And so why does this rotation thing mean anything, right? So if I had like a fixed point, right, so a like hinge or whatever, and so you've got a rod. Let's just say that is B. Okay, let's just say that doesn't move, that's B. A is now moving relative to B, right? Well, what I'm just trying to say is, okay, let's say the velocity of A that way, right? And this is an integer, right? The velocity A is equal to the velocity. Velocity A is equal to velocity of A relative to B because B is moving, right? So if this is not moving, this is just the rotation. Trying to do like this. So this is following a circular path as it's rotating. That's the circular path. And so this is a straight line in the end. Just like how this is a straight line. But it's only a straight line because each step you're moving to the right and you're rotating. Moving to the right and rotating. Moving to the right and rotating. So that's the general plane motion. But for the rotation, you can't Yeah, you have to treat one end as like fixed because you're only doing the rotation.
So what if you like?
Okay, that's a good question. So I'll draw you the other animation tracks. If instead we were interested in general plane motion of B, right? So again, it follows that same path, right? There, but if instead we were focused on velocity of B, so we actually care about finding this path, right? It's equal to the velocity of A, right? So we're following the path there, following the path there.
So following the same transition.
Wait, I'll just explain last one, and then I'll actually parallels, right? So now this time we're fixing A. Okay. We're saying that path reduction methods. So the other one was going this one's going that way. This one's going that way.
So here our piece is an A and here our B.
Yes. So this is going down, so it has to be counteracted by something going up, right? This one's going to the right, so it has to be counteracted by something going up.
You do a bunch of extra stuff.
And then the total horizontal movement. Yeah. And do you see how these subscripts are flipped? Because that's flipped that, that's flipped like that, that's subscript flipped that. Just have a ponder. Okay. Sorry. Took longer than I expected. All right. Let us continue. So let's do a question. Okay. All right. Oh, sorry. Let's not do a question yet. Let's talk about angles. Okay. So when you have a right angle triangle, you can use sine, cosine, tan, all good. All right, because one of those angles is already known if it's a right angle. If you don't, so if you have a triangle that looks like this, then you have to use either sine rule or cosine rule. Okay, so let me give you a refresher of how they work. Okay, so sine rule is basically saying if you have a triangle, right, with these three side lengths A, B, C, and these three angles alpha, beta, gamma, so you've got 6 things basically, right? You've got 6 parameters or variables or whatever. This is like a triple equality, right? A triple equation thing, right? And you can isolate 2 out of these 3 equations, right? And equate them with each other, okay? So for example, if we wanted to ignore that part of the equals sign, right? Let's just delete this for a moment. We now are left with 4 parameters, right? And we need to know 3 of them to work out the 4th, okay? So that we only have 1 unknown algebraic variable to solve for, okay? So, for example, if we knew alpha, beta, and b, right, if we knew alpha, beta, b, you can solve for a, the side length, for example. Another thing you could do is if you knew a, b, and beta, you can solve for alpha, right? So that's kind of how it works. So there's kind of 2 scenarios, right? You might be interested in finding an unknown side, or you might be interested in finding an unknown angle, right? Finding an unknown side is all good. You're not going to run into any problems. Solving an unknown angle, though, what's going to happen is it always gives you the acute angle, right? So this is a problem in certain scenarios. So for example, if you have a triangle that looks like this, and you want to work out alpha, and you can see alpha is greater than 90 degrees here, what happens is when you punch in these side lengths of 8.7 and 10.2, right? When you punch in these side lengths, as well as, you know, this angle, and you're trying to solve for alpha, you actually get this angle over here, right? You get the acute angle 73.8, and the reason is because it treats it as if this side length was this side length over here. And it always gives you the angle that's less than 90 degrees. Okay, so just be careful. This is just use your intuition when you're solving these angles. Okay. Cosine rule. How it works is basically involves 3 sides and 1 angle. So for example, if I just delete 2 of these angles, it basically works like this. In the case where you're solving for either the side length A or the angle alpha. Okay, so if you rearrange this expression for a side, right, then like side length A, for example, you need to know these 3 things. So you need to have B, C, the other 2 side lengths, and the opposite corner's angle. But if you were to try to solve for alpha instead, you need to know all 3 side lengths, okay? So that's kind of these 2 expressions. So yeah, that's just a recap of how those work, and you won't run into any issues of cosine rule. Any questions? This is finding angles based on geometry. Okay, so relative velocity, right? Let me just get on my notes quickly. Let's do our first question then. Okay, so how a lot of these questions are set up is through links. Specifically, it's 2 link questions. So we've got 3 points, right, and 2 links. We've got this link, OA, and we've got this link, AB, okay? We've also got this cylinder thing that causes B to move. So this thing's fixed, and then it extends this rod such that the point B moves down, okay? I want you to pay attention to like how this system will move, right? Think of it like a little animation. So it's going to do this, and it's going to do this with the other link, right? And this point B is going to shift down, right? So it's going to move from here to here, right? So this is the velocity of B, right? We're told what the velocity of B is, right? We're told that VB is 0.6 meters per second. And we're also asked to calculate the angular velocity, which we're going to call omega OA, of link OA. Okay, so so basically think of it like inputs and outputs, right? So in this particular question, the input is VB, so the downwards velocity of point B, and the output that we want to solve for is omega. Okay, so rotation about O. Okay, and in the next question, you'll see it's kind of flipped, right? So we're told what the velocity at O is, and we're solving for the linear velocity on the other side. Anyway, cool. So first thing we're going to do is figure out the geometry or the angles of everything. Okay, so yeah, basically if we call these angles alpha, beta, gamma, we have to call the opposite side lengths A, B, and C, okay? Or, well, this is just kind of what you do in your head. And then we need to apply either cosine law or sine law. So remember, right now we know all 3 side lengths, but we don't know any of the angles, right? So this would imply that we should use cosine law, right? Cosine law works if you have 3 side lengths, okay? So we can do that. And let's solve for beta first, okay? So beta is basically the opposite side, right, is 90 mil. 130 is side C. 180 is A, right? So we're just substituting in everything, right? Okay, and then we're going to rearrange and solve for beta. Okay, so this gives me beta is equal to 28.3164 degrees. Okay, so now we know 3 side lengths and 1 of the internal angles, right? And it's up to you whether you want to use cosine law again, right? Just reapply it for a different angle, or if you want to use cosine law, okay? I choose to use cosine law simply because it's shorter, okay? So here I'm comparing C with B, okay? So C with B and the associated angles beta and gamma, right? So we know C, B, and beta, and we don't know gamma, right? So our sine law and how we apply it is going to be this fraction, right? And we're solving for gamma, right? So these are your side lengths and angles. We're solving for gamma. Okay, like so. All right, so for this last angle, right, now that we know 2 out of the 3 internal angles, like the simplest thing to do, right, isn't cosine law or sine law. It's understanding that a triangle, all the internal angles add up to 180, right? So when you know that, you do 180, subtract the other 2 internal angles, right? And it gives you the remaining angle, and the remaining angle is 108.436. So I deliberately saved the obtuse angle for last because they can't screw anything up with sine law, etc. Okay? So that's how you would handle that. So now we've got all 3 internal angles, right? The next thing we're going to do is set up a velocity vector. And what this involves is so the way that we set up, we're going to set up something called a velocity triangle, right? Which I'll tell you what that is. And the way we do that is we analyze each link. Okay, so we've got this link OA, and we've got this link AB, right? Or BA, or whatever. Here I've drawn it as BA. Okay, so yeah, and this one I've actually drawn as OA. Okay. All right, so let's just talk about the first link. Okay, so we know this point is fixed, right? And so the other end's the one that's moving. Okay, we know that the way that the whole system is going to move is going to cause a clockwise rotation about point O. Okay, and then that implies to us that the velocity has to be going down and right in this particular scenario, right? Because it has to be at 90 degrees, whether going that way or that way, to the rod, right? And in the case of going clockwise, it has to be going down and right, okay? The other thing is understanding the geometry. So beta, right? Again, we worked out what beta was, right, over here. But it's understanding that if you have a 90-degree angle, right, from the lever arm to the velocity vector, we want to know the angle that the velocity vector is coming off of either the horizontal or the vertical line. And so what we do is we just add 90 degrees, and that gives us the fact that the velocity vector is coming off of beta at, coming off the vertical at an angle beta, right? So that's important, right? We set up the vector and the direction. Okay, the other thing is, now we're looking at link BA. So I've decided to do BA, but to be honest, you can actually do AB as well. I'll tell you how that works differently in a bit. But let's just say, because remember, I've basically cast a link from O to A, and I've cast a link from B to A, okay? So what I've done is kind of like this and like this. But this is just the way that I did the question. You can actually do the question just fine if you do this as well. I'll explain the difference in a bit, all right? It's to do with how you set up your relative velocity triangle. Okay, so if you set it up this way, the way that I've drawn it, you'll know that link BA is in general plane motion, okay? It's moving, and then there's this rotation component, right? So if you imagine that this isn't moving for a second, this is the still part, okay, and it's going to be spinning that way, and then this is, you're adding on the translation as well, right? So that, yeah, anyway. So what we're interested in, essentially, is these velocity vectors, right? So we're interested in the velocity of A relative to B, right? And we know that this is at a 90-degree angle from the rod, okay? And we found out how much the rod is inclined from the horizontal. So we do a similar thing where this has to be 90 degrees or perpendicular from it, right? Oops. And so if we add 90 degrees, we get that the velocity of A relative to B is coming off the vertical axis at gamma, the angle. Okay, and then the other thing we know is that VB is just downwards. The reason we know that is because we're told in the question that the cylinder pushes the point B just like straight down, okay? So now we know the direction of these three vectors, right? That's the important thing. Because when we set up a velocity triangle, right, we can set it up like so, okay? So this will be the triangle, and then the graphical interpretation of it, right, or the graphical way to represent it is like this. Okay, so we're setting up a triangle like so. So with this triangle, the velocity vectors are basically coming off the same point, right? And sorry, you'll see here that it says VA relative to O, but you have to remember that VA is equal to VO plus V A relative to O. And when VO is 0, so O is the fixed point over here, then these two things are equal, okay? So I kind of take this a bit too liberally. So let's just say that's VA for now, okay? Anyway, so VA is coming off at an angle beta from the vertical, and then we know that VAB is coming off an angle of gamma from the vertical, right? And so that leaves this remaining angle alpha. Okay, so let's just take a step back and think about what we know and what we don't know from this velocity triangle. So we know what VB is, right? We're told in the question what VB is. We also have worked out these angles, okay? What we don't know is this, and we don't know this. Like, we don't know the magnitudes. We know its direction, okay? But then we have to think to ourselves, what do we actually care about? Okay, and the answer is we only care about VA, which is also VA relative to O, okay? And the reason we care about that is because ultimately we're trying to work out omega, right, OA, which requires VA, okay? So knowing this, we basically need to set up a sine rule, right? Because this is another triangle, right? This is just another triangle with angles. But instead of physical geometry, the side lengths of the triangles are the vectors' magnitudes, right? Okay, so we can work out VA if we just isolate it, and we know these three other variables, right? So we know that VB was 0.6. We know that this angle was 43. We know that this angle was 108. Okay, and that gives us that VA, which is also equal to VAO, is 0.4333 meters per second. Okay, so once we figured that out, this allows us to plug into a formula for omega. Okay, so it allows us to plug into this, right? So this is what we worked out a second ago. And we also know the rod has this lever arm, okay, and the lever arm is 0.13 in terms of meters. So when we solve for omega, we get 3.333 radians per second going clockwise. Does that make sense? No? Okay, kind of? Okay. So this is the relative velocity method, what we just did. Okay. The next method I want to explain to you is the instant center of rotation method. Okay, so this basically comes down to basically finding a point that's off your free body diagram, which represents a point which doesn't is fixed but is rotating. Okay, so what do I mean by that? First, let's consider the question. If a bar AB, so this is the bar, has an angle. Oh, sorry. You know what? The other thing I didn't do is I didn't tell you what happens if you cast this link the other way. Okay, so if you cast this link the other way, what you'll get is something like this, right? So this will be instead RAB, okay? And then you'll get this. You'll get this, omega AB, right? And then this, you just pretend it's not moving, right? In this particular drawing. And then you get instead VB relative to A, okay? You get VB relative to A. And with that, instead of using this formula, you'll end up doing VB is equal to VA plus VB relative to A. Okay, so you will get this triangle instead, which would be going the other way, right? So instead of, let me just reiterate this. So this triangle looks like this, right? You still cast those two velocity vectors, but your relative velocity vector is going to point the other way. So it'll be going that way. Okay, so again, we don't care about this, right? So all we care about is finding VA, right? So whether you go link BA or whether you go link AB, it will give you the same answer. So it doesn't really matter. Okay, it's just how you set up this relative velocity vector. Okay, so that was like a little tangent. I'll go back on track. Okay, so instant center of velocity method. What does this mean? Okay, so let's just think about for a second how these two links, how these two nodes, and I guess the links will be moving. Okay, so let's just clarify the language. This is a link. This is link AB. This is a link. This is link BC. What do I mean by node? I mean nodes being the ends of the links, right? So A, B, and C are your nodes, okay? We know that node A doesn't move at all, okay? And then node B and node C are the two nodes which are actually moving, right? So that's pretty much how every single question is set up. You're gonna have two moving nodes, basically, right? So in this particular question, we're told that there's some kind of rotation, right? That is known for link AB, okay? That's the first thing. And we're told that we need to solve for the velocity of C, right? So how fast is node C moving, right? Well, the first thing we can do is figure out the direction, right? Because without knowing the magnitude, we can already figure out the direction, because if we move this forward in time, we can tell that this is the way that it wants to rotate, and therefore it has to be moving left, right? So this has to be moving left, like so. We just don't know its magnitude yet, right? But that's fine. We just need to know its direction for now. Okay, the other thing is the velocity of B, right? We don't know its magnitude quite yet, but we can know its direction because it can only be going one of two ways, right? Is it going to go up and left, or is it going to go down and right? Well, we know that it has to go up and left because the rotation is causing this link to go up and left, right? And 90 degrees to the rod, right? So we know the two directions of the velocity of the nodes, right? We know the directions. And so what the instant center of rotation method is saying is what we have to do is cast a lever arm, basically, which is perpendicular to these two velocity vectors until the two velocity vectors coincide. Sorry, until these lines of action basically coincide, right? Wrong word. Until these lever arms coincide. Until the lever arms coincide. So that's one lever arm, and that's another lever arm, and there's a point which it coincides, and that point is called the instant center of rotation. Okay? So that there is the instant center of rotation. I've just called it D. Okay, sometimes in the lectures you'll see it called IC, which is the instant center, or ICR. But anyway, so that's what I called it. Okay, the other thing is to note that these two distances are not the same. This is just a trick of the eye, right? If I was to exaggerate this triangle, it might actually look more like that, okay? So this side length is not the same as this side length, okay? Just keep that in mind. Okay, the other thing is saying that these two velocity vectors, or these two nodes B and C, are going to move are going to rotate about the instant center either clockwise or counterclockwise, right? So in our case, we can see that it's going clockwise, right? So these two arrows are pointed going clockwise, okay? And they're going to move with the same angular velocity around point D, okay? So you'll see that omega D is going to be equal to omega dB, and it's going to be equal to omega dc, okay? So this is going to have the same angular velocity as the velocity going there, okay? Okay, so that's kind of the setup. So now we just have to find VB in order to start doing some maths, right? So we can find that through knowing that this is fixed over here, and knowing that VB, right? So the movement at this end is equal to the angular velocity, which we're given, right? The angular velocity multiplied by the lever arm, okay? And the lever arm here is 200 mil, but it's the same thing as 0.2 meters, okay? Giving us 1.2 meters per second, okay? And that's moving up and to the left. Okay, so now we know what this is. The next step is finding these angles. So you can actually find these angles, and once we find these angles, we're going to be able to work out these lever arms, right? Okay, so how do we find these angles? Well, the first one is basically, if I draw this, right? This triangle looks something like this. I might exaggerate it. It might look something like this, okay? So the first thing to note is that we know that this node B is moving to the left, and its lever arm is perpendicular to this, correct? So that's at 90 degrees. Okay, and we're told that this link, right? So this is the only physical object here, right? This link is 30 degrees inclined from the horizontal. And so if we do 90 minus 30, we find that the remainder is 60. So that's the internal angle at this corner of this triangle. Okay, and then the other one we know is basically, I'm going to draw this off the screen a bit. Over here, this is 45 degrees, all right? So that's oh, sorry, that's C, isn't it? Fuck, sorry. Okay, so over here is B, right? And that's A, right? So basically, if you imagine like a right angle triangle here, this angle is 45 degrees, okay? And so that leaves the remaining one as 180, subtract 45, subtract 60, all right? And that gives us 75. So now we know all three of these angles of this triangle that sets up over here. So the other node is this imaginary point called the instant center of rotation, which I'm going to call D, okay? So that gives us geometry. The other thing is, yeah, we're going to be solving for these two side lengths, right? So we're going to call this like a cast distance over here, and a cast distance over here of RDB and of RDC, okay? And then we're gonna do something later, which is to do with the angular velocity around D, okay? So the first thing we do is we have to figure out what RDB and RDC are, okay? I said R so many times in a row. And the way that we do that is knowing that this rod is 0.5 meters long, right? And then we also know the angles, and therefore we can use sine rule, right? So the sine rule relationship is this, okay? So we can basically, for the first scenario, we can equate these two in blue, right? And if we equate those two in blue, you can solve for the remaining unknown, right? Like the unknown there. The other thing we can do is equate this with this one again, right? Giving us this unknown, okay? So these two numbers are 0.683 meters and 0.612 meters, okay? So in other words, this one's slightly longer than this one, Okay. Any questions so far? Okay, so we've found the geometry, and now it's just a matter of finding out. Okay, so basically we know this, right? So now we know this. This is sorry, that's V. We know VB. We know RDB now, like we've solved that. We also know RDC. So we've solved for these three things. What we need to do is we now need to solve for omega D, okay? Because this is going to stay consistent for these two as well as these two, okay? So if we figure out omega D, right, through rearranging this equation, right, because we know what VB is, it's 1.2, and we know what DB is, it's 0.612. We rearrange for this, okay? We rearrange for this, giving us 1.96 radians per second, okay? And then we say, sorry, and then we can ultimately work out this one, okay? So we work that out through the fact we know this one and the fact that we know this one. So now we've just worked out the velocity of node C. Does that make sense? So that's the instance center of rotation method. And I would say that it's easier than the relative velocity method. What makes it kind of hard is trying to understand this trying to understand this like invisible point out in like space, okay? Because yeah, this is kind of like hard to visualize at first, basically, right? But once you get a grasp of it, this is generally the student's preferred method to solve these questions. Okay, let's talk about acceleration to dynamics, okay? So, and let's just talk about cross products. So you might choose to do all these questions using cross products instead of the dot product system that we've kind of been doing. So when I'm talking about the dot product system, I'm talking about the fact that we've been doing stuff like V is R dot gamma, for example. So gamma, what the hell? Omega, right? And then we kind of consider the directionality separate to this, you know? We consider this as, you know, clockwise or counterclockwise, or, you know, this being like going that way or that way, and etc., right? So we kind of just fudge the maths a little bit and then point the directions according to our understanding of how the physics works. That's kind of what we've been doing. If we do it the cross product way, right, so doing it mathematically coherently, right, this is how we do it. So just a little recap on these unit vectors and how cross products work for them. Basically, if you cross product any of these scenarios on the left, you get a positive, and if you cross product any of these scenarios on the right, you get a negative. Okay, and the way that you can remember this is by visualizing a circle. So you can have I, J, and K vectors like so, and depending on which way around, whether it's clockwise or counterclockwise, you go on the circle, you get a positive or a negative result. Okay, so what do I mean? So let's just draw this as like a little circle thing, right? I'm just going to copy this so I can do two examples, right? So in the first example, let's say we do I cross product J. We get the other one, so we continue around the circle, right? So remember, the order which you do everything matters, right? So I cross product J is not the same thing as J cross product I. Okay, so you have to go like in a certain direction. If you do I cross product J, you get K, but specifically you get positive K, right? And the reason is because you're going the clockwise direction in the circle. If you go the other way around, right? So for example, if we instead do J cross product I, right, and we're going counterclockwise, right, we get negative K, right? You can see that that's the difference between the first and the second scenario, right? So if you go I cross product J, you get positive K. If you go J cross product I, you get negative K. Does that make sense? Kind of. So yeah, just keep in mind this little diagram. This is a good way to remember whether you can get a positive or a negative when you do a cross product, okay? Okay, so when you do acceleration dynamics, you need to basically do the velocity dynamics first. You need to already solve for things like linear velocity and angular velocity. That needs to already be done in order to work out things like your linear acceleration and your rotational or angular acceleration. Okay, so you need to do these before you do these. Okay. Okay, so basically, let's do a quick recap on circular motion. All right. So this is kind of how it works for. Ooh, just want to click here. Back. Yeah. Add page. Okay. So imagine I have some rope in my hand, like so, like that, and I'm swinging a ball which is tied at the end of it around in a circular path. Okay, so I'm swinging around, swinging around. The path might look something like this, right? And when we account, so I'm swinging it that way, so the angular velocity is going that way. The linear velocity at this point, let's say the middle of that ball is point A. The linear velocity at A is going to follow the tangent of the circular path. Okay, so we call this the tangential direction. So if we were to look at it in terms of directions, right, we've got the t direction. So t direction is tangent to the path. The other thing is acceleration, right? So acceleration, you've got some component of the acceleration, which is gonna be in the tangential plane, right? So if it's accelerating, right? If it's angularly accelerating, then the linear acceleration of A, in terms of its tangential component, is going to follow the same path as, the same line of action as the velocity vector, okay? But then there's also going to be a component that pulls in, okay? So the linear acceleration of A, specifically the normal component, is actually going to pull in. And what this is going to mean is that the net, or the diagonal, or the hypotenuse acceleration, linear acceleration of A, right, is actually going to be diagonal, right? So you can add the normal and tangential components together and get that diagonal, okay? And what you'll find is we point the normal direction outwards from the center of rotation, right? So if we casted the lever arm, for example, being the string's length, out from the middle, that's going in the positive normal direction. But what happens with the normal component of the acceleration is it wants to actually pull in, right? So that's your whole like centripetal or centrifugal force or whatever it's called. And that's how this object A actually stays on this path, right? Because it has to pull in, right, in order to stay on this path. All right, and that's circular motion. So why is this important? It's because when we're doing our acceleration dynamics, the rotational component of acceleration is represented by the relative acceleration, right, between, so like A relative to B, for example, right? And then that can be broken up into the portion, the linear portion that's going tangentially and the linear portion that's going normal, okay? And you'll see that this one follows this formula and this one follows this formula. And the tangential one is going to be a cross product between your angular acceleration and the lever arm. And then your normal component is going to be negative, which is important, which I'll explain in a second. The angular velocity squared dot product with the lever arm. Okay, so why is it negative? So it's negative because remember, this arrow is pulling in, right, in the negative normal direction. Okay, so that's why this negative is very important. Okay, this one's just the other one, the order flipped around. So A gets flipped to B, and then subscript gets flipped around as well. Okay, so that's fine. Let's do a question. Okay, so I'm going to go over the velocity dynamics kind of quickly because I want to focus on acceleration dynamics for this question. So as you know, as I mentioned, you need to solve for the velocity dynamics first anyway, before we can even figure out the acceleration dynamics, okay? So for this particular question, right, we have two moving points just like we did before, except these 2 points are going to follow the incline. So we have pretty predictable paths, right, for where we're going. We're also told the decline angle from the horizontal of this second surface, right? We're also told the length of this rod, okay? And we're also told the initial velocity, right, of A. We're told it starts at 4 meters per second. And we're also told the acceleration of A is 6 meters per second squared. Okay, what we don't know is the velocity of B, which we can solve using velocity dynamics, and then we can solve for VB, which we can do through acceleration dynamics. Okay, so if we use the instant center method, and the instant center method is really nice here because it makes a perfectly equilateral triangle, right? So the point of rotation is out here, and it forms this lever arm that makes a perfect equilateral triangle with the rod, okay? And so each of these internal angles is 60 degrees, okay? So this question is particularly nice. What we need to find first is basically the angular velocity of C, right? So the rotation. How we can do that is through this, okay? So that's VA, right? So we know what VA is, and C doesn't move, right? So when we say velocity of A relative to C, we're saying the velocity of A relative to something that's not moving, which is just the same as saying the velocity of A. So this is 4 meters per second, and then this is 0.6. Okay, so that's the lever arm of here to here. Okay, so once we compute that, we get 6.67 radians per second, and we know that this is going this way, so counterclockwise. Okay, and velocity of B, right, because all of these lever arms are the same length, you're going to see some pretty familiar numbers. So we can input our angular velocity around C, and then we input that lever arm, which is again the same as this lever arm, giving us that the velocity of B is the same. Okay, so this VB is 4 meters per second, just like how VA was 4 meters per second. Okay, cool. Okay, so we want to solve now for the angular velocity of AB. Okay, so this is R AB, and the angular velocity is omega AB. So we want to find omega AB, right? So again, we can plug this in, 0.6. This is 0.6. As you can see, you get the same thing because the lever arms are all the same, right? Okay, so what we've done now is we figured out the angular velocity, we figured out the velocity of B. What we don't know is we don't know the angular acceleration, and we don't know the linear acceleration of B. So these two things are unknown. Okay, so how are we going to solve this? What we do is we use the relative acceleration formula, okay? And then we are going to split up the relative component into its normal and tangential, sorry, the other way around, the tangential and normal components, okay? So we can plug in our numbers, all good. Okay, on the left-hand side, what you'll notice is that the linear acceleration of B is actually further split up into two subcomponents, okay? And so why is that? It's because even though we don't know what this is, right? Let's just draw this as an arrow. We don't know what the acceleration of b is. However, we do know the angle, right? And we know that this angle is 30 degrees. And so this has to be the hypotenuse cosine 30 degrees. And this has to be the hypotenuse sine 30 degrees, right? So why we've split it up into its horizontal and vertical is because, as you can see with the unit vectors, it is useful for us in a bit when we're comparing just the directions to use unit vectors. Okay, so here's the horizontal component, and here is the vertical component. Okay, so it's going down for acceleration, all right? Okay, so our tangential component goes there. Our normal component goes there, okay? And so let's see what we're actually doing, right? So with the tangential component, it's the cross product between this component, which has a unit vector of k, and it's positive, okay? And it cross products with two terms, okay? One is positive I and one is negative j. And then the other, the normal components all dot products, okay? So let's handle the cross product first, okay? So this one's a cross product, this one's a dot product. For the cross product, let's draw our little schematic. So we have k, let's draw it, I, j, k, right? We're starting at k, so we start here, and we're going to cross product first with I. Okay, that's going to give us j, and we're going clockwise on this little circle, right? And so it's going to give us a positive number. Okay, so remember, sine 30 is just 0.5, and so what we're going to get is 0.6 times 0.5 is 0.3. Sorry, I've flipped these in my little working out. Yeah, that's better. So we get 0.3 alpha ABJ, okay? So this cross product with that, right? Okay, and then we're gonna do K. So let's draw another one. We're gonna start with K, and we cross product with J this time, except the J is negative, okay? We go this way, and we're gonna get something for I, right? And normally when we go counterclockwise, we get a negative, right? But because we're doing a negative times a negative, we actually get a positive. So that's this one. You can see there's a negative here. So we're doing a negative times a negative, and so we actually get a positive, and that gives us 0.52. Okay, great. Okay, let's do the dot product next. So dot product, this one's going to be a negative number multiplied by a positive number for I, and that gives us negative 13.3 I. Then we go a negative number, dot product with a negative number, so that gives us a positive number, which is 23.096. So that's in terms of J. All right. Next, we're going to group like terms, and there's only going to be two like terms here. It's going to be the J terms. So we can simplify this to 17.096 J. And the rest is going to stay the same. Okay, so what we're going to do now is we're going to compare the horizontals with the horizontals and compare the verticals with the verticals, okay? And what's going to happen is, if you think about it, we have two unknowns, right? We have the linear acceleration at b, and the other unknown is the angular acceleration, right, of AB. So since we have these two unknowns, right, you'd think that this is not solvable, but we're going to use basically simultaneous equations to solve this. So we can set up two equations. So the first equation is based on the horizontals, and the second equation is based on the verticals, right? So if we just compare the I terms, this gives us the horizontals, right? So it tells us that, AB on the left is equal to all this stuff. And then this is your second, term or whatever. Okay, so now we've actually rearranged it such that we have an expression for just a, b, right? So that's this one. If we substitute that in, right, we now get everything in terms of alpha, right? So we've got alpha over here and over here. Okay, so now we've got an expression just in terms of alpha, and so alpha is solvable, and it gives us this negative answer, right, in radians per second squared. And the negative here actually means something. It means that we're dealing with a with a clockwise spin. Okay. And then the linear acceleration is this. Okay, and the way that we solved for that is we plugged alpha back into equation 1, and then we were able to solve for equation 1, which was framed in terms of linear acceleration. Okay, so now we answered the question basically. We were able to get the angular acceleration as well as the linear acceleration. Okay, so that's pretty much the whole workshop. So yeah, basically, if you look through my notes, this is rigid body kinetics, which, as I mentioned at the start of the workshop, may or may not be in your test. Good luck. Okay, I'll see you next week.